Hello, and welcome to the lecture on 1.6. Today we're going to talk about complex numbers. First, let's define what a complex number is. A complex number is an expression of the form a plus bi, where a and b are real numbers and I squared is equal to 1. The real part of the complex number is a. The imaginary part of the complex number is b. Now I want to note here that the imaginary part is just b. It's not bi, it's just b. It's the coefficient on the I term. Two complex numbers are said to be equal if their real and imaginary parts are equal. Example: the complex number c equals 2 minus 3i has real part 2 and imaginary part -3. A complex number with 0 real part is called purely imaginary. A complex number with 0 imaginary part is called real. Now I want to make a note here. I squared is defined to be -1, as we have here in the definition of the complex number. What that means, though, is if we multiply both sides of this by I, then on the left we get I cubed, and on the right we get -I. And then if we multiply by I again, we would get on the left I to the fourth, and on the right -I squared. But remember that I squared is equal to -1, so we would have a -1, which then implies that I to the fourth is equal to 1. All right, the next thing that we're going to do is we're going to cover the arithmetic operations of complex numbers. So let a plus bi and c plus di be complex numbers. We'll start with addition here. A plus bi plus c plus di is equal to a plus c plus b plus d I. What we do is we add the real parts together, so a plus c, and we add the imaginary parts together, so b plus d, b plus d. Subtraction will be the same. A plus bi minus c plus di is going to equal a minus c plus b minus d I. Again, we subtract the real parts, so a minus c. C is negated because of this negative here. And we subtract the imaginary parts, b minus d, b minus d. Multiplication. Now, multiplication is exactly how we would multiply two binomials together. Remember that you have to distribute a couple of times in order to actually multiply two binomials together. We do a similar thing here, where we would distribute the a plus bi in, and then we would distribute each of the corresponding parts, the imaginary and complex part. So here we would get c times a plus bi plus d times a plus bi times I plus di times a plus bi. And then, of course, we distribute in again, and we get ca plus cbi plus adi plus bdi squared. Note that we have an I squared here because the i's multiply together. Now, we take our two real parts, AC and BD. This becomes a real part because I squared becomes -1. So we would end up with AC minus BD, our real part, plus our imaginary part, which will be BC plus AD. If you factor the I out of both of these terms, it's another way to think about it. Thus we have the multiplication of a plus bi times c plus di is a times c minus b times d plus b times c plus a times d I. Let's do an example of this. So let's let z1 equal 3 plus 2i, z2 be negative 1 minus pi I, and z3 equal 2 minus I. So part A, we want to find z1 plus z2. Now we just add their corresponding complex numbers. So 3 plus 2i plus negative 1 minus pi I. So 3 plus 2i plus negative 1 minus pi I. Now, we can drop the parentheses, and the reason that we can drop the parentheses is because we're automatically at the addition level. So this will become 3 minus 1, adding the real parts, plus 2 minus pi I, adding the imaginary part. So this, of course, then becomes 2 plus 2 minus pi I. Now you might be asking yourself, why can we not combine these 2's? It's because this I is connected to both of these. Remember, this is the imaginary part, this is the real part. We can't combine them because we have a multiplication here, and this multiplication is higher in the order of operations than addition. Z1 times Z3. So we're looking at 3 plus 2i times 2 minus I. Yes. Now we can just distribute like we did when we showed the multiplication rule, but we can also FOIL. First, outer, inner, last. And multiply all of those together. 3 times 2 plus 3 times the negative I plus 2i times 2 plus 2i times the negative I. 3 times 2, of course, becomes 6. This is minus 3i. 2i times 2 is going to be 4i. And then the two i's multiply together to give us an I squared. So we'll have minus 2i squared. Now remember, I squared becomes negative 1. So this ends up being 6 plus 2. If I move the 2i squared over, the I squared becomes negative 1, and it'll cancel this negative, make it a positive. So we'll end up with plus 2 when we resolve this entire thing. So we have 6 plus 2 plus 4 minus 3i. We can combine the imaginary parts as well. 4 minus 3 will become 1. 6 plus 2 is 8. Whenever we have a 1 for a coefficient, it's already understood, so we don't need to write it. Definition. The complex conjugate z bar of a complex number z equals a plus bi is z bar is equal to a minus bi. Note here that all we're doing is negating the imaginary part. That's how we find the conjugate of a complex number, is we negate the imaginary part. A stays the same, we negate the b. That's it. This will play a role as we move into the next part of this section, where we're going to end up multiplying and dividing complex numbers. And the next part of this section is going to deal with dividing complex numbers. To simplify the quotient a plus bi divided by c plus di, we multiply the numerator and denominator by the complex conjugate of the denominator. So if we have a plus bi divided by c plus di, what we want to do is multiply top and bottom by the conjugate. So we would end up with a plus bi divided by c plus di times c minus di. Remember, the complex conjugate negates the imaginary part. The important thing is that we get a real number in the denominator. What will happen here in the denominator is that we have a difference of squares. So each term will be squared, and we'll have a subtraction between them. So this will become c squared minus di quantity squared. And in the numerator, you can multiply this out to be ac plus bd plus bc minus ADI. Now remember, when we square the I, we're going to get a -1. So this will become AC plus BD plus BC minus AD times I divided by C squared. Now when we have this I squared, it will become 1 and it'll cancel this negative. So we'll end up with C squared plus D squared. Let's do an example of this. Say that we want to rationalize the denominator, and we have a quotient 1 minus 2i divided by 4 plus I, something like this. We're going to multiply top and bottom by the conjugate of the denominator, so 4 minus I, 4 minus I, like this. Then in the denominator, we should end up with 4 squared minus I squared. Now again, remember I squared will become -1 by definition. On top, we have 4 plus 2i squared. The 2i times the -2i times the -I. Minus I, it's the 1 times the I. Minus 8i, that's the -2i times the 4. So again, the I squared becomes a -1, so we get 4 squared plus 1, which will become 17. And in the numerator, we have another I squared, which will become -1. So we have 4 minus 2, become 2. And then we have a -I minus 8i. So if I have -1i here and another -8i here, then I have in total -9i. And that will be it. The denominator is rationalized. It's a real rational number, so we don't need to do anything more. I want you to try a problem now. Rationalize the denominator. 1 plus 3i divided by 3 minus I. All right, I want to do one more quick example of rationalizing the denominator, because not all problems are equal. Suppose that we had something like this, 3 minus 4i divided by 2i. Okay, note we can still take the conjugate of the denominator and multiply. That would be to negate the imaginary part, so we would be negating the 2 and multiplying. But we don't need to. All we need to do is multiply top and bottom by I. Whenever you have a purely imaginary number in the denominator, multiplying by I is enough. Because there's no real part for this I to distribute, we will not end up with an imaginary part in the denominator. Our denominator will be real. So if we multiply by I over I, we end up with 3i minus 4i squared. Now again, I squared is equal to -1. So this will negate this negative. It'll cancel this negative out. Divided by 2i squared. Now again, I squared is equal to -1, so we'll end up with a -2 in the denominator. So I'll end up with something that looks like this. 3i plus 4 in the numerator, -2 in the denominator. Now I can move this negative out to the front. So I end up with a -4 plus 3i in the numerator and just a 2 in the denominator. Okay, the next topic of discussion is going to be square roots of negative numbers. Let r be greater than 0, then the principal square root of -r is the square root of -r equal to I root r. The two square roots of -r are I root r and -I root r. Let's do an example of this. actually do a couple here. What we're saying here is that if we have the square root of a negative number, something like this, then what we do is we pull this negative out and create an I in front. So this would become I times the square root of 4. Now we can take the square root of 4 because 4 is positive, and we end up with just 2. So the solution to the square root of negative 4 is just 2i. Now part B is a little bit nuanced here. Now part B is in the context of equations. So suppose we have x squared is equal to negative 9. For simplicity, I'm going to take the square root of both sides. Now when I take the square root of x squared, I should get the absolute value of x, but I'm going to write it as x and put my plus or minus over here. So we end up with something that looks like this. X equals plus or minus the square root of negative 9. Now remember, when we have the square root of a negative number, we can pull this negative away and create an I in front. So we end up with plus or minus I square root 9. Now the square root of 9 is of course 3, so we end up with x is equal to I times 3, and x is equal to negative root 3i. Now I need to make a note here, because there is a common misconception. When performing calculations that involve square roots of negative numbers, start by writing them with an I. Now there's an incorrect way, and there's a correct way of doing this. Suppose that we wanted to multiply the square root of negative 2 and the square root of negative 5. Now the incorrect way would be to combine these into a single radical and say negative 2 times negative 5, and that gives us the square root of 10. Of course, this is not equal. Okay? The correct way would be to write each one with an I in front first. So if we have the square root of negative 2 times the square root of negative 5, we would end up with I times the square root of 2 times I times the square root of 5. Then when we multiply these together, the i's multiply to an I squared, and then we can combine the 2 and the 5, square root of 10. But, of course, I squared is equal to negative 1, so we end up with a negative root 10. Okay, so the last thing that we're going to talk about is complex solutions to quadratic equations. So first, let's recall the discriminant d is equal to b squared minus 4ac. And if d is less than 0, then the quadratic has no real solutions. Now the key word here is real solutions. We still have two complex solutions, we just don't have any real solutions. So let's go ahead and recall what the quadratic formula is. X is equal to negative b plus or minus square root b squared minus 4 times a times c all over 2a. Now, our discriminant is here. When we have a negative discriminant, you see that we would get a square root of a negative number. This will yield a complex solution. Let's do an example of this here. Suppose that we want to find the solutions to the equation x squared plus 2x plus 2 is equal to 0. Now, you could try to factor this. It's not going to work, but you could try. But what we're going to do instead is use the quadratic formula. So if we use the quadratic formula, we need our a, b, and c. Our a is 1, our b is 2, our c is 2. So x equals negative b, so we get negative 2, plus or minus the square root of b squared, 2 squared is 4, minus 4 times a times c. So 4 times 1 times 2. All over 2 times a, which is just going to be 2, because 2 times 1 is 2. So this reduces to negative 2 plus or minus the square root. 4 minus 4 times 2 is 8, all over 2. Now, 4 minus 8 is equal to negative 4. So we end up with negative 2 plus or minus square root of negative 4 all over 2. Now here, we need to remove this negative, and remove this by adding an I to it. So we have then x is equal to negative 2 plus or minus I square root 4 all over 2, and the square root of 4 is of course 2, so we end up with negative 2 plus or minus 2i all over 2. Now here we can cancel our 2's, but first I'm going to factor a 2 out. So I end up with 2 times negative 1 plus or minus I all over 2. Now, the reason I needed to factor it out is because we're dividing by 2. I need the inverse operation of division, which is multiplication. 2 is now being multiplied by the rest of the numerator, and the numerator is being divided by a 2. So this number is being multiplied by 2 and divided by 2. So the 2's can cancel. Now, you have to be careful with this. Don't try to cancel a single 2 in the numerator with a 2 in the denominator. You have to factor the 2 out first. So our answer ends up being negative 1 plus or minus I. I have one last example for y'all. And I like these types of problems. I think they're interesting. Pi powers of I. Now, the nature of I reduces its power down to between 0 and 3. What I want you to do is try to find I to the 1001th power. So how do we go about this? Well, first we need to recall the powers of I. Remember, I squared is equal to negative 1. I cubed then becomes negative I, and I to the 4th becomes 1. Now, we're going to abuse the fact that I to the 4th is equal to 1. And I'm going to rewrite my I to have a power that's a multiple of 4. So I to the 1001 power is equal to I to the 1000th power times I. Remember, when we have the same base and we multiply, we add the exponents. So I can break up a power into two things being multiplied together where the powers sum to the original power. So here I'm breaking up I to the 1001 power to become I to the 1000 times I. Now I'm doing this specifically because 1000 is a multiple of 4. This is very important in these types of problems. This is the key. This is a multiple of 4. Okay, so now what I'm going to do is abuse the property that I to the 4th is equal to 1. I'm going to rewrite this as I to the 4th to the 250th power. Now remember, when we have a power to another power, we multiply. Those two are equal. So we can go from I to the 4th to the 250th to being I to the 1000th, or we can do the opposite. I to the 1000th is the same thing as I to the 4th to the 250th power. Let me carry this I down. Now remember, I to the 4th is equal to 1. So this then becomes 1 to the 250th power times I. Now, 1 to the 250th power, all that means is 1 times 1, 250 times. And we can come up with that multiplication pretty easily because 1 is the multiplicative identity. It doesn't change anything when you multiply by 1. So if I multiply 1 by itself 250 times, it doesn't change anything. I'm left with 1. And then 1 times I is, of course, I. So I to the 1001 power reduces to I to the 1st power. That's going to be it for today. I will see you all in the next lecture.